SwayamPrabha. Digital India. Educated India.
Good morning, dear friends. You must be tired by now. We have completed takeoff, climb, cruise, landing. We have also discussed something about twin engine takeoff, twin engine landing. These are the primary things we discuss in the performance course. Of course, it includes maneuver. We have also covered maneuver. However, you will appreciate during our discussion, we have assumed one thing very implicitly, and that is the aircraft is stable in flight, right? And when I say aircraft is stable, what do I mean by that? What do we mean by saying that aircraft is stable? And if I try to again pose this problem, we have distinct phases of flight. By now you know. This is takeoff, this is climb, cruise, landing, then maneuver. Now let us take a case when here I am cruising, where lift equal to weight and drag is balanced by thrust. We have been always telling that this is unaccelerated flight, unaccelerated rectilinear flight. One thing was net forces or net force is zero. The summation of all the forces, aerodynamic force, gravity force, and thrust, they are balanced. So we say net acceleration is zero. Also we assume implicitly net moment acting on it is zero. Now in this part of our extended lecture, we will ask a question. Suppose an airplane is flying like this, and if there is a disturbance means suppose it's going like this and there is a upward gust. What this upward gust will do? It will induce angle of attack. And the question now is whether this airplane will be stable. That is, whether the airplane will try to manage this disturbance, counter this disturbance, or it will just become unstable and topple. So we are basically trying to focus on a question. Suppose it is going like this and there is an upward gust of wind. Let me draw a little more so that there is a clarity. Upward gust coming. And this will naturally induce angle of attack. It will change the vertical component. So it is going like this, the upward gust, so there is a additional angle of attack. But I want to fly on a particular angle of attack which was decided by the condition lift equal to weight, right? So we'd like to know whether it possesses a stability or not. That is, once it is disturbed, whether it has initial tendency to come back to the equilibrium or not, that is, come back to the condition of lift equal to weight, thrust equal to drag or not. So we'll be asking two questions in very specific manner. One is initial tendency, and second is within a finite time whether it is coming back to equilibrium or not. So what are the two questions we'll be asking? One is whether it has initial tendency to come back to the equilibrium or not. Second is in finite time whether it is indeed coming back to the equilibrium or not. Having tendency doesn't guarantee that it will come back to the equilibrium. What actually happens? You see that the moment there is an upward gust, there is a disturbance, I write delta alpha, small alpha. We are all talking about small angle disturbance, right? The moment there is a small alpha, you will understand this lift will get modified. Lift will become L plus delta L. Drag will become drag plus delta D. So if it has an initial tendency to come back to equilibrium, then it has to do something to ensure that there is an initial tendency to reduce or to make this delta L to 0 so that it comes back to the lift, and initial tendency to make delta D 0 so it comes back to the equilibrium condition where lift equal to weight, thrust equal to drag. If I now take you back to class 11, 12th, when you were talking about or learning the beginning about stability, which diagram comes to your mind? If you close your eyes, I'm sure all of you will be able to recall a very popular diagram. What does this diagram remind you about? Or what really comes to your mind? If I see the dotted line, what is the dotted line? I say this is the equilibrium line. You could see here, net force acting on the body is 0 because one is weight of the body and there is a reaction from the surface, so they balance each other. So there is no acceleration along this vertical line, so we say it is at equilibrium. Similar situation is here, this is also at equilibrium. And if I again try to make it more explicit, this is the W weight and there is a reaction from the surface, and R minus W equal to 0, R equal to W, and that is what is the consequence of it being in equilibrium. And similarly, there are no forces in any other direction, which is unbalanced. But now, please understand, we want to know about stability. So we want to see its behavior vis-a-vis a disturbance. You may be having so many friends, few will be your special friends. Among yourself, you must be discussing, this man is very sensitive. This man becomes very violent. He or she encounters slight disturbance. Don't you think so? You might have seen one of your friends could be reacting very violently for small jokes. And few of them will be, whatever you do, they don't react. They remain in their state of calm. So those friends who have this character of not getting disturbed, or even there is a disturbance, they know how to manage their original state of mind, still remain calm. We will say he is a stable person. But there are persons who may slightly you cut joke about them and they will just become violent. They may start fighting. So in our language, we will say that man is unstable. Now, if I try to correlate this to this diagram to see whether this body is stable above this equilibrium or not, what I should do, I should give some disturbance. So, if we give a disturbance like this, that is, I am just displacing this body here and leave it. What will happen? Immediately you see this body has initial tendency to come back to this equilibrium because of this weight component, and then it overshoots. Again, the moment it overshoots the equilibrium, immediately there is an initial tendency to come back to the equilibrium. So all the time it has initial tendency to come back to the equilibrium as soon as it is disturbed from the equilibrium. So any system which, when disturbed from the equilibrium state, if it has initial tendency to come back to the equilibrium, the catchword is initial tendency, then we say that system has static stability. Is it clear? That is, think of another situation which will be more illustrative. This is also from your daily life and you have seen your textbook. This is a mass spring system, and if I hang it, there will be a slight extension, and at this point, whatever force or the weight of this mass is balanced by the spring force in the opposite direction. So if I draw it, it will be, this is the mass, this is the mg acting like here, and spring force K into x. X is the displacement. So you know that Kx is equal to mg, and that is the equilibrium point, and there are no other unbalanced or imbalanced forces. So I call that is the equilibrium. Now I want to check whether this system is statically stable or not. So what is the rule of thumb? You introduce a disturbance and release it. Let's see what happens. So I introduce a disturbance, I stretch it to some distance, let's say delta x, and then release it. Stretch it and release it. What will happen? If you further assume that the spring is a linear spring and there are no medium here, no medium. So what will happen? See, the moment I stretch it from the equilibrium, this mass will be acted upon by an opposing force or a spring force in the opposite direction. So which will have an effect showing initial tendency of this body to again go back to the equilibrium. If a mass spring system is stretched through mass, then you see the moment it crosses the equilibrium, immediately a force will come kx in the opposite direction, which will have a tendency to take this mass to the equilibrium. So this system has got initial tendency to come back to equilibrium. So I said this system is also statically stable, like that system. But what will happen here if there is no medium? This will have an initial tendency, so this kx, so this will go and it will come somewhere here, right? And it will go on oscillating like this. Okay, as it goes there, again, the moment it crosses the equilibrium, there is a restoring force. It starts applying the moment it crosses the equilibrium line. Okay, by inertia it goes to this point, and again so it goes on oscillating like this. And now you know that by definition of static stability, the moment it crosses the equilibrium, it has a force which tries to restore the equilibrium. So this system is statically stable, but nobody guarantees that it will come back to the equilibrium. I am talking of a case where there is no medium. So it will go on oscillating like this. So there will be conversion of potential energy and kinetic energy. Okay, but think of a situation if I put this inside a cylinder. And put some oil or water, then what will happen? If I stretch it, since it is crossing the equilibrium from here, immediately kx, the restoring force will start acting. So it has the initial tendency, so it will exhibit static stability, try to go towards the equilibrium. Now because oil or water is there, so it will start oscillating in a manner that amplitude will go on reducing, because a lot of friction will be there with the water or the oil. Or we'll tell that this system will have some sort of a damping force. Damping force means, when the force is proportional to the rate of the motion, displacement. For this discussion, it is good enough to know that you need damping where the force will be proportional to the displacement, rate of displacement, x dot, or if it is a moment, then it's proportional to the angular rate. Let's say theta is the angle, angular rate. More important thing, damping is proportional to the rate of change of the state of the body with reference to the equilibrium. And what we are talking about static stability, there the force, that is for static stability, we are talking about that force proportional to the displacement, because F equal to minus kx, or moment if it is proportional to the angle. theta I am using a notation as an angle. Theta dot is angular rate. Mostly we will be talking about static stability in this part of this course. Let us try to ask ourselves what we have discussed up to this point. We have talked about static stability, and the catchword is initial tendency. To come back to equilibrium state. Now coming back to aircraft. When it comes to aircraft, we are in this part of the lecture, perhaps in this course, we are focused towards angular stability. That is, if aircraft is like this, if the angle is disturbed, whether it has initial tendency to come back to the original angle or not. Okay? That is, if the aircraft is here, flying like this, if I disturb it, whether there will be a restoring moment which will ensure that the moment the aircraft crosses the equilibrium, the restoring moment will come to ensure there is an initial tendency to come back to the equilibrium. To that part we will be talking in terms of static stability for the aircraft. And if I try to model it, I will model it like this. This is the aircraft, and I put a coil spring. For a mass spring damper system, we modeled it like that. Okay? Here we say, if I disturb it, it has the initial tendency to come back to equilibrium. Here, disturbance will be, I disturb it like this. The moment I disturb like this coiled spring will generate a nose down moment, which will ensure that it has initial tendency to come back to equilibrium. This is what we will be discussing in this part of the lecture. Maybe another one or two more lectures on that. But try to see this carefully. If there were no coiled spring, then I will not get any restoring moment. But when an aircraft is flying, there are no spring like that. This tendency, this initial tendency through a moment has to be generated by interacting with the air. Okay? And that is where the whole designer will be focusing on to make an aircraft statically stable. So he has to identify a part of the airplane which should be responsible primarily to give that nose down moment if the angle of attack is increased, a nose up moment if angle of attack is decreased, to ensure there is an initial tendency. We are trying to search for this answer. What is that component? Okay? So question 1, we are addressing static stability. Question number 2, again let us see this model. So question number 1 is, we are trying to address issue on static stability, finding that component of airplane which will provide static stability. And question number 2 is very, very important, related to controlling the aircraft. That is, through this schematic model, suppose there is a spring type which I have represented here. By now we know that there won't be any physical spring when the airplane is flying, right? The spring-like action has to be generated by interacting with air, and we have to identify which component will do that job, right? Let's see that is available. So that is what is represented here. So it will resist any change of the attitude of this airplane. But now tell me, you are flying at a speed v and it has a corresponding CL, so the lift equal to weight. Now you want to fly at a higher speed, still maintain lift equal to weight. So what do you have to do? Since the speed is higher, now you have to reduce the angle of attack because you have to reduce the CL. Reverse way, suppose I am flying at a lower speed and CL is say 0.5, so let's say angle of attack is 4 degrees. Now you want to fly at a lower speed, So your CL has to be more, so you have to raise the angle of attack. So you have to ensure that depending upon speed, depending upon the altitude, you should be able to change the angle of attack of the airplane, or you can change the attitude of the airplane. But you have made the aircraft statically stable. So any moment you want to change it, it will say nothing doing, I'll try to come back to the equilibrium. This is the real problem. So what you have to do, if you have to really ensure that the airplane now have an attitude like this, and this spring is still there as a model, I'm trying to, because somebody is generating the restoring force, because, or restoring moment in this case, because it is statically stable. It is discouraging any change. So if you now want to really fly at this angle, so you have to hold it. So you have to generate a force here which will give a moment, and this moment should be equal to the restoring moment because of this spring. So now at this attitude, net moment again will become 0. So this becomes your another equilibrium. And at this equilibrium, since the aircraft is stable, if there is a further disturbance, the aircraft will try to maintain this equilibrium. So what is the message? If something is statically stable, if you want to go to another condition, for example, from one angle of attack to another angle of attack, I have to ensure a moment we should overcome the restoring tendency because this is statically stable. And this is what is called a control problem. So not only static stability, now second question is how do I control the aircraft? Is the question clear? If something is very highly stable, in our language it is difficult to control, because if it is highly stable, it will not like to change from its own equilibrium. It will resist to go to another equilibrium because highly stable. So you have to apply a huge control moment to really take it up. So there is a limit. How much stability or static stability you want so that you can comfortably control the airplane. And that is what is the biggest challenge for the designer, because finally you understand this airplane will be flown by pilots, with a human being. Even if you say nowadays so many actuators are there, control system is there, you have to also think of the actuators. You should not overtax the actuator. You should not unnecessarily overload the actuators. That's not a good design. So we'll be now explicitly see what do you mean by static stability, how do we give static stability to an aircraft, like a spring back action type for ensuring static stability, and also how do we control the aircraft. If these two things we understand, and if we understand their relationship, job is done. Okay? Thank you.